Okay, hello everybody. My name is Dmitry and I'm a moderator for today's talk. And today Michael Wormit will start our series of webinars with his talk on symmetry in libtensor design and usage. So please, Michael, go ahead.
Yeah, thank you, Dimitri, for the nice introduction. And I'll start with a short overview on what symmetry in libtensor does. Before I go into explaining how symmetry is stored with any tensor you create in libtensor and how this interacts with the tensor blocks. And then I go on explaining how the symmetry operations work and give a short, a really quick example in the end how this all plays together and how the code would then look like. All right, so let's start with the overview. So as Evgeny already told us in his talk on libtensor, every block tensor which you can create in libtensor can have symmetry stored. Stored together with the actual tensor data. These symmetry elements then reduce the amount of storage you need, or the amount of blocks you need to store by introducing like maps between different blocks. So here in this picture, you see, I don't know, can I use a mouse? No. All right. In this picture, you see on the left-hand side, this square of blocks. These represent the blocks in a block tensor. So that would be a two-dimensional block tensor. And together with the symmetry, you only need to store the orange blocks, while without symmetry, you would have to store the whole block tensor. And this is how we, this is the reason why we introduced symmetry. And for the user to access the symmetry and add symmetry to a block tensor, you have this control object from which you can request the symmetry using the request symmetry. This would be a read and write access to the symmetry, or you can have read-only access. That would be a request const symmetry. One thing one has to take care of with this read-write access is if you add a symmetry element to a block tensor when the block tensor has already been created and filled with data, then these blocks which become invalid due to the symmetry element won't be deleted right away. So there might be some additional storage in the block tensor while it exists. It's not a memory hole because as soon as the block tensor gets out of scope, these blocks will be deleted. But if you don't take care as a user, so if you add a symmetry element after you have already data in the block tensor, then you might end up carrying around additional data with you. So best thing is use the request symmetry only before you first add data to a block tensor. So this is the part how symmetry interacts with a block tensor on the data side. And then we have the tensor operation side, how symmetry and symmetry operations interact when you perform a block tensor operation. So usually you have some input tensors, which are shown here on the left-hand side, which all have block data and symmetry data, and they are combined in a block tensor operation, which might be a contraction or an addition or whatever, into a results tensor C on the right-hand side, which also has a symmetry and some block data. And the first step, which happens in the block tensor operation, is the determination of the result symmetry. And therefore, the symmetry A and symmetry B is combined using a symmetry operation, which will I explain how they look like afterwards, later in the talk. and the result symmetry C is determined. After that, from the symmetry C, so the result symmetry, we now know which blocks have to be calculated for the tensor C, and these are then these blocks are then evaluated in parallel to get the result tensor C for the block tensor operation. And this is like the big overview or the big picture how these two, how the symmetry and the symmetry operations play into the block tensor operations we have in libtensor. So now let's start with the symmetry data. How is the symmetry information stored inside a block tensor? So first of all, what are the different classes which we have in the symmetry? So the main object in every block tensor is the symmetry class or symmetry object, which consists of a list of symmetry element sets, which are simple containers for symmetry elements of a certain type. So currently we have three different symmetry element types. One is the permutation symmetry element SE perm. Another is the spin symmetry element SE part. So the name SE part stems from partition symmetry, and we use it as spin symmetry. There might be other use cases for this symmetry element, but yeah, for now we only use it as spin symmetry. And also we have a label symmetry, which we use for point group to represent point group symmetry in the tensors. These three classes are all derived from the symmetry element interface, which is an abstract base class. And one property these symmetry elements have to implement is the type, the symmetry element type, which identifies which for symmetry element set and symmetry what kind of symmetry element is in there. And every symmetry element set only has symmetry elements of one type in there. That's just the grouping. This is how symmetry data is stored inside a block tensor. And now coming to the symmetry element interface, how does it look like? So we have several abstract functions which have to be implemented for every symmetry element type. So there's first of all this get type function, which returns the type as a string. Then we have a clone function, which just gives does an exact copy of the current symmetry element. We have the check compatibility function, or is valid BIS it's called. That's that checks if a block index space which is passed to this function is compatible with the symmetry element, or the other way around, if the symmetry element is compatible with this block index space. That's necessary to do certain sanity checks during a calculation. Then the last three functions, which are on this list here, these are specific, or these are necessary to determine certain blocks. These blocking structures, which blocks are unique, which are allowed, which can be reproduced by applying some transformation onto a block. So the first one is allowed, has an index, and the symmetry element should determine if the block which refers to this index is allowed by the symmetry element. The other two are two apply functions. I start with the second one. Apply gets an index variable, a block index, and this applies the symmetry element to this index and modifies this index if the symmetry element does so. The first one is an amendment of this second function, and it has an additional tensor transformation as argument. That's also an output argument, and the symmetry element should set this tensor transformation if, for example, for a permutation, the block should be permuted when the symmetry element is applied. So, as an example, if you have a rank 2 tensor, so a two-dimensional tensor, and you have a permutational symmetry, and then block 0, 1, if you call apply on blocks 0, 1, on the index 0, 1, that would change the index to 1, 0, and for the tensor transformation, you would get this permutation 1, 0 plus a scalar transformation of 1. If it's permutational symmetry, if it's symmetric with respect to the permutation, or if it's antisymmetric, you would get a -1 with this tensor transformation. Maybe I should add that the tensor transformation consists of a permutation and a scalar transformation would be, which in for doubles or real numbers would just be scalar multiplication. So, and whenever you come up with a new symmetry element type, you would have to implement this interface for it to work with a libtensor. And there are some more things which you have to implement, but I'm coming to this later. So now coming to our existing symmetry elements. So we have the permutational symmetry, as I said before, that consists of an index permutation and a scalar transformation. So taking the example from before, this rank 2 tensor, if it has a permutation symmetry which is symmetric, then it would the permutation would be permuting 0 and 1, and the scalar transformation would be just multiplying by 1. If you have complex numbers and a similar symmetry but Hermitian symmetry, then you would have the scalar transformation being the complex conjugate. This is it, more or less. And then here's an example setup for 2-electron integral A, B, C, D. If you want to set the respective permutation symmetry elements for this, well, this integral has permutation symmetry with respect to A, B, and C, D, exchanging both indices at the same time. And it has permutation and antisymmetry with respect to interchanging A and B and interchanging C and D separately. So what we start off with, we create a scalar transformation, two scalar transformation, TR1, which is multiplication with 1, that is for the symmetric permutation, and with -1 for the antisymmetric ones. Then we create 3 permutations. One is interchanging A and B, that's the P10. Second one, interchanging 3 and 2, that's a permutation CD. And then we have interchanging A and B with C and D, that's the third one. And well, creating the permutations doesn't do anything. You have to set them up properly. So that's the next 3 lines. That's P10 permute 0 and 1, permute 2, 3 for P32, and permute 0, 2, and 1, 3 for the third one. And then you create the 3 permutation symmetry elements here. And you can then add them to the symmetry object, which I'm showing a little bit later. Yeah. So this is for the permutational symmetry. Next symmetry element we have is the partition symmetry. The partition symmetry is used currently in libtensor mostly to represent spin symmetry, but there might be other use cases in future. So we've made it as flexible as possible, but yeah, so since we only had one example which we could work from, it's mostly targeted at spin symmetry. And what partition symmetry does is it divides every dimension of a block tensor into bigger partitions, which I have denoted here again on the upper right corner. There's two partitions, so in both directions. So these are the dashed lines. So you group 4 blocks in this case into one partition each. And the requirement is that the block structure within each partition is identical. And that's the only way it can work. And with this grouping, we can now define mappings between the different partitions or mark certain partitions as forbidden. So here again an example. So if you want to, for example, create an excited state vector, like a CIS vector for a triplet state, so CI singles vector here, BIA. First thing you have to do, you have to set up a mask to mark which dimensions are going to be partitioned. Because, for example, for the MO coefficients, you might have just one. You might just want to partition only in one direction and not in the second one, because the AO index doesn't carry alpha or beta spin. So, but in this case, both indices carry spin or are to be partitioned. So we create a mask which is all true. Then we create the partition symmetry element for 2 dimensions, type double. You have to pass it the block index space of the tensor, the mask, and the number 2 defines how many partitions you have along each dimension. So if there were, for example, a 4, you could imagine that would represent like the for a relativistic calculation, the alpha beta spins, large components, small components. So that would be 4 a division into 4 partitions in each dimension. So, but in this case, we only have 2 because we only have alpha and beta spin. And now we have our partition symmetry. This is still empty. It's just the basic structure set up. We have to create the mappings and mark forbidden blocks and so on. So next thing we do is we create a scalar transformation with -1, since for a triplet, the all alpha partition should be the negative of the all beta partition. So that's for our map later. And then we have to create indices for referring to the different partitions. So I left out where we set the index to the respective values, but I00 should refer to the 00 block, 00 partition, I01 to the 01 partition, I10 to the 10 partition, and I11 to the last one. So that would be, if you think about a spin, that would be alpha alpha, alpha beta, beta alpha, and beta beta spin partition. And then you add a map from the alpha alpha to the beta beta block with the scalar transformation -1. That's the triplet. As forbidden, since they don't contribute. These are for spin flip states, for example. And that's it. This is the partition symmetry element set up, and now you can add it again to your symmetry object of your tensor. Last symmetry element we have currently implemented is the SE label. It's probably the most complicated of all, at least to set up. The idea behind SE label is that each block in every dimension carries a label, and the symmetry element defines a rule how to evaluate these labels for every block, and to determine by this evaluation which blocks are allowed and which blocks are forbidden. To be more specific, for point group symmetry, it's kind of like straightforward to see this. You have the labels are the irreducible representations of the orbitals, the indices, or the blocks we are referring to. You have to have sorted your orbitals into the blocks so that in each block you only have orbitals of the same irreducible representation. And then with these labels attached along each dimension, you add a product table to the symmetry element. The product table contains the standard product table, how to multiply to reduce representation, what comes out. And then the evaluation rule in this most simplest case tells you if the product of 2, 3, 4 labels contain or irreducible representation contains, for example, the totally symmetric irreducible representation, then the block is allowed, otherwise it's forbidden. That's the idea behind that. The rule how to evaluate the block labels is set in this evaluation rule, which is a part of the SE label implementation, while the block labels are contained in the block labeling class, which is also internally stored in the SE label. To set up, here's an example how to set up such a symmetry element. You have this is an example for the Fock matrix of a molecule with C2 symmetry. So first you have to create an empty symmetry element with the block index dimensions, which tell you how many blocks are there in this block tensor. So how many blocks are along each dimension. That's something you can get off a block index space. And the second parameter, which I call PG name, is a simple string which contains the identifier of the product table you are going to use with a symmetry element. The product table itself is not directly stored inside the label symmetry element. It's stored in a global object from which the symmetry label element can request the product table whenever it's required. The next step is in this sequence is you have to get the labeling object out of this, the symmetry element and set up the block labels. So this block labeling element or object has a function assign, and the assign function takes as first parameter a mask. The mask tells the block labeling object which dimensions you are currently assigning. So in this case, since for the Fock matrix I and J are identical dimensions, we create the mask as being both true, but you could also have different masks here, like a 0 only, or the first only the first index true, or only the second index true. And then we assign to the first block in both dimensions the A label, which refers to the A irreducible representation, to the second the B label, which refers to the B irreducible representation, to the third again an A, and to the fourth B. So assuming we have also spin symmetry here. The first two would be A and B in alpha spin, and the second two would be A and B irreducible representation in beta spin orbitals. And then at last, when you have set up the labeling, you can set the rule. And there are different functions how to set a rule. And the most simplest one is this line I put here. So that's just set rule with an irreducible representation, in this case A. And this means that whenever the product of the two labels of a block contains the irreducible representation A, so the totally symmetric one, then then this block is allowed, and otherwise it's forbidden. That's this is the most simplistic way to set a rule, and it's also the most commonly used. At least if as long as you are with abelians point groups, then everything is more or less just this set rule, and everything's fine. All right. So this is so much for the symmetry elements. Oh yeah, I forgot. What you also have to do for the essay label, you have to set up the product table sometime. You only have to set up a product table you want to use once in your whole program, and then you add this product table to this global object from which the label elements, the label symmetry elements can request the product table. So, and for the C2 symmetry, this is how you set this up. You start off with creating this identifier, the point group name. I tend to use the real name, so what we would call them, but you can use any string here. That's not restricted. Then you have these label types, which are just an alias for unsigned integers, A for 0 and B 1. That's the first two or the only two irreducible representations. You need a vector of strings, which give also names to the irreducible representations. And then you set up the point group table by passing it the point group name, this vector of strings, so this vector of names for the irreducible representations, and the totally symmetric irreducible representation. That's specific to the point group table because the point group table needs to know this totally irreducible representation to do some sanity checks. And then you set up the point group table by calling these add product function. So A times A. So for the product function, this first argument, second argument in the product, and then the result. A times B is B, and B times B is also, no, that's wrong. That should be an A. Sorry, that's a typo. The third line, there should be B, B, A as arguments. And this gives you the product table I've drawn in the comment on the right-hand side. So for A times A is A times B is B, B times A is also B, and B times B is A. And then you add the product table to this product table container, which is the global object where you store all your product tables. You can add as many product tables here as you like. Usually we have only one or maybe two of these product tables in a calculation, but there's no limit to this. And the only requirement when you create a symmetry label element is that the unique string you pass to the symmetry label element has to be a string or has to be an identifier of a product table which you have previously added to this product table container. So this is done in QChem currently, somewhere at the beginning of CCman2 or ADCman, when we read the symmetry information from QChem and import it into the context. At this point, this symmetry is set up and added to the product table container. All right. Now, a quick remark on the determination of canonical blocks. So, as I said in the beginning in the overview, the symmetry is used to determine a minimum amount of blocks which have to be stored inside a block tensor. And this is strongly related to the concept of orbits, which are implemented in, for example, in this orbit class. And so the idea is that the symmetry elements form a generating set for a group which acts on the block indices or on the blocks. You can view it both ways. And an orbit is the set or a set of block indices which can be retrieved by applying different symmetry elements one after the other. So, for example, down here at the bottom, I have this. I have made an example for rank 2 tensor. This is the example I've been using throughout already, which has a permutational symmetry with respect to dimensions, a spin symmetry where the alpha block equals to the beta block, while the other twos are forbidden, and a point group symmetry element, so that essentially only the two or four diagonal blocks of the alpha and beta blocks are allowed. And what you see then here is, all right, for the first block, so that's the upper left corner, the block in the upper left corner. I just show you. So here, if you, I just went back to this SE part symmetry element because here is essentially the same tensor which I'm talking about. So I1 would be the first block up there, and this is mapped by the symmetry element for spin, that's S2, to the 11th, which is the first one in the beta block. So the first block in alpha is mapped by S2 to the first block in beta, and that's that would be one orbit in this case. Another orbit would be the second element, which is forbidden due to point group symmetry in this case. But this is also mapped by this permutation symmetry element to the fifth block in the whole tensor, and then it's by combining S1 and S2 is mapped to another one and mapped to another one by again applying the permutation symmetry element. And this is how we construct these orbits. And you can see, so for the first I1, this is allowed by all symmetry elements, and it's mapped. It can be mapped onto I11. So I1 is something which we store. I11 we don't store. So these two blocks have been, well, we have covered them with the symmetry element. We go to the next one. So I2 is forbidden due to S3, and then we go through and see which other blocks map onto I2 can be mapped onto, and we know that all these are also forbidden. And so we continue until no blocks are left. And this gives us a minimum, in this case, a minimum of 2 blocks which have to be stored in this block tensor. Yeah, and one thing, the lowest index in an orbit, so the block with the lowest index in an orbit is usually the unique block which is stored, so I1 and I6 in this case. So much of how the symmetry data looks like, how you set this up, and how this connects to the tensors, to the block tensors. Now, next thing is we come to the symmetry operations, because without the symmetry operations, the symmetry would sit there inside a block tensor, and you can nicely add data to a block tensor. But then when you combine 2 tensors in an operation, then without the symmetry operation, there wouldn't happen anything. So the result tensor would have full symmetry, all blocks, no symmetry at all. And yeah, to allow for the result to have also proper symmetry, we have these block tensor, these symmetry operations. And here is the design of the symmetry operations. So first of all, for any symmetry operation you might need, there is this base class symmetry operation base, from which you have to derive your symmetry operation. So on the right-hand side, there's an example, the direct product of 2 symmetries, one with rank n and one with rank m, gives us a result in n plus m, rank n plus m tensor or symmetry. And this is derived from the symmetry operation. And then internally, you have for every symmetry element that exists and every symmetry operation, you have these symmetry operation implementations. Because like combining two symmetry elements into one might differ or differs from symmetry element to symmetry element type. So as a result, you need a separate implementation of an operation depending on the symmetry element type. And to put these 2 things together, which I separated with this dashed line, the symmetry operation base is the overall symmetry operation, which does the loop over all types which are present in the input tensors and calls the respective symmetry operation implementations for these symmetry element types. And again, down here you see an example of how you would create a symmetry operation implementation for a direct product and a permutation symmetry. That's just the header of the class, and what you have to implement I come to on the next slides. So for example, now you come along and you realize, all right, what's in the tensor isn't what I want for a symmetry operation. So you say, all right, I need a new symmetry operation. And to get this, you first have to implement the symmetry operation base. And therefore, you need a constructor. And this usually has to, gets the inputs, the input functions. So I put here an example for SO permute, which is a symmetry operation which permutes some indices in the symmetry or some dimensions in the symmetry. So you get the input tensors or the input symmetries and some possible parameters, which in this case is just a permutation you want to apply to the symmetry. The second function is, the second thing you have to implement is the perform, which performs the operation and returns the result symmetry. So you pass it usually a parameter for the result symmetry, and then you implement whatever this symmetry operation should do. And at this level, this perform function should loop over all symmetry element types present, construct a parameters object of type symmetry operation params, which I'm showing later, and then call the specific symmetry operation implementation for a given symmetry element type with this parameters object. And this specific implementation of the symmetry operation will then do the actual work. So this symmetry operation base is essentially a wrapper around these symmetry operation implementation, because otherwise you would this would be in every block tensor operation. You would have to call for every specific symmetry element type, you would have to call the symmetry operation implementation, which is kind of a mess. Anyway, the second step when you add the symmetry operation is you now have to add symmetry operation implementations for every type for which the symmetry operation should be used. And therefore, you have to implement this class symmetry operation implementation. Essentially, there's just one function which has to be implemented, which is this perform function, which takes the symmetry operation parameters class as with a template parameter for this symmetry operation. This is really specific to the respective symmetry operation, and you have full freedom of what to do there with the symmetry operation parameters. The only requirement is that it should contain the inputs and the outputs and the parameters you have for the symmetry operation. And then this function should loop over all symmetry elements of the current symmetry element type and construct the result symmetry element or elements, depending on what kind of symmetry element type you have, and add them to the output symmetry object. Yeah, specific examples, there are several of them in the symmetry directory of libtensor. So there you have full freedom, and well, just take a look at this and see what it's like. Yeah, and the parameters class has to be defined for every symmetry operation, and as I already said, it comprises the input symmetries, output symmetry, and some additional parameters, whatever are needed. This varies in our case. For the symmetry operations we have already implemented, this varies depending on what the symmetry operation is supposed to do. So now we have put some effort into what symmetry operations are actually required for to perform arbitrary block tensor operations. I mean, we know that there are a number of block tensor operations, and there might also be additional block tensor operations coming up, and we wanted to have as few work as possible to implement these symmetry operations. So we thought what's like more or less a minimum set, and this is hopefully the best, well, the minimum set we came up with. I'm not sure if it's complete, and probably you can find an example where these set of symmetry operations don't work. But anyways, I'm going through these now and explain what they are doing. So the most simplest symmetry operation is SO copy, which just copies the symmetry from one symmetry object to another without changing it. That's just needed sometimes. Then we have a permute indices or SO permute object, which permutes the dimensions of a symmetry without changing the symmetry. That's helpful if you do an assignment between two tensors and the indices of one tensor are permuted there. That's what this is for. Then we have a direct product. This glues together two symmetries and as a direct product. So you get from n and m dimensions, or rank n and rank m, to rank n plus m as a product, and then there's a direct sum which does the same thing as a sum. First, I thought that having one of these two is sufficient, but it turned out like it's really different depending whether you have a product or a summation. What happens to the symmetry elements there, especially the label and the partition symmetry are quite sensitive towards whether it's a product or a sum. The next two are, start off with merge dimensions. Merging dimensions means you have, like, for example, 2, 3 dimensions and combine them into one. The original idea for this one was taking the diagonal of a matrix or of a higher rank tensor. That would be a merge. But now, when generalizing it, I figured that, for example, an addition operation can be represented as taking the direct sum of two symmetries and then merging the indices together, like merging 1 and 1, 2 and 2, 3 and 3, and so on together. This would be the merging dimension. Reducing dimensions is more or less the same, like merge, but in addition, you also sum out the dimension. So reducing means you merge like 2 or 3 indices together, and then you reduce out or sum out this one dimension which is left over. That's essentially what the reduced does. And doing this merging and tracing or summing in one step is helpful because you can make use of certain optimizations here. The next one is symmetries. That could also be represent like this is symmetrizing dimensions, like, or symmetrizing two symmetries, like A plus A prime or A transpose would be a block tensor operation which uses symmetries as a symmetry operation. Doing this in one step is also helpful for optimization, but otherwise you could also do it with a direct sum in the merge. Last thing is the apply. We have some block tensor operation which is called BTOD apply, which applies an arbitrary function element-wise to a block tensor operation. And this one can't properly be implemented by any of the above, so this apply function is for this case only, so the symmetry operation apply. I think it's not much used currently, but I have some ideas how to use this in future, so that's the reason why it's there. And then how do these this minimal set of symmetry operations map onto the block tensor operations? I've listed here a few of the operations we have in libtensor. So the first line is element-wise addition, the second is element-wise multiplication division. Then we have the contraction, scalar multiplication, taking diagonal, taking a function of a tensor or matrix, and extracting a lower dimensional matrix from a higher one by fixing a certain index of the higher dimensional tensor. And all these map onto these block tensor operations you see here. So BTO dead and BTO copy for element-wise addition and copy. And then these use, as I, like, this is the example I already told you. So the addition would do first, so the symmetry operation or constructing the result symmetry would first do a direct sum of the two symmetries and then do an SO merge of all the dimensions onto each other. So dimensions from tensor 1 and dimensions from tensor 2, moving them onto each other. together, because there's, for especially for SE label, there are some specific pitfalls here why you have to do them in one step and not in several steps, like this merge. You could think, well, okay, I first merge the first of A and first of B dimension together, and then second, and so on. But this doesn't work. So you have to do this all in one go. For the element-wise product, so the block tensor operation is BTOD mold or EW mold, and then you have the SO DIR product, so taking the direct product of the two symmetry symmetries and then doing an SO merge at the end. For the contraction of two tensors, you again use a direct product, and then you use this SO reduce I was talking about before, where you, in addition to this merge, you also sum over this remaining dimension or trace it out, so to say. Scalar multiplication is essentially a copy, so the symmetry operation is BTOD scale, and well, the block tensor operation is BTOD scale, and the symmetry operation is maybe SO permute if you, in addition to scaling, also permute the tensor. For diagonalization, that's BTOD diag, and the symmetry operation is an SO merge. BTOD apply, so applying a function or taking a function of a matrix element-wise, in this case, would be SO apply, and the extract is another use case for this S over reduce, because, well, in this case, we are not reducing out, but you can the S over reduce symmetry operation, there you can specify the range of indices which you're tracing out, and if you specify as a range just one element, then this would mean an extract, would be equivalent to an extract. So this is how this reduction of the dimensionality of the tensor is mapped onto the symmetry operation SO reduce. Yeah, and now I'm just presenting a few examples, or well, essentially just one example of how you would use this now in a program. So, well, as you usually do, you would create a block index space and a block tensor, like you see here in the first part. So you need something to add the symmetry to, and then what next step would be you would try to obtain the symmetry before adding any data, because otherwise you might run into some additional storage which is not required. Or, well, you have to know what you're doing if you add data first and then request and then add the symmetry element. So yeah, to obtain the symmetry element, you create this block tensor control object on this tensor you've created before, and then you use the request symmetry function to retrieve the symmetry element, and then you add the symmetry elements you have created somewhere in between, and how you create them I showed you before with the symmetry data. So you create a permutation of symmetry element using a permutation and the scalar transformation partition. You would create the partition first and then add the mappings, or for the label you would create the label, then set up the labeling of the symmetry element, and then at the end set the rule how these labels are evaluated. And also how to use the symmetry operations. So I have led you through like how you would implement a symmetry operation, a new one for a new, usually for a new block tensor operation, and then how are you going to use the symmetry operation inside a block tensor operation? Well, what you do is, again, you have two input tensors, which are here BTA and BTB. You create control objects. In this case, read control objects would be sufficient. You request the constant using the constant symmetries using request const symmetry. And then for the output tensor, you have to use a writable block tensor control object to retrieve the symmetry for the result. And then you use these three to perform a symmetry operations on them. So in this case, I have chosen SO direct product, so the direct product of the two symmetries. This would be sym A, sym B, and no permutation, so you don't change the order of the indices in the result. So it's just first indices of A, then indices of B, and then you call the symmetry operation with the result symmetry, and this will internally again call the respective symmetry implementations for the permutational, partition, label symmetry elements, and so on. Yeah. And that's essentially it. That's all I wanted to tell you today. And if you're interested in some more detail, I'm happy to answer questions and also give another webinar on more details on how the symmetry operation implementations are done.
Okay, thank you very much, Michael, for a very nice talk. So do we have any questions from the audience or from the online attendees? Yeah, if you have any questions, please write it here in this chat.
I have one small.
Yes, so maybe you come here.
Hi, Michael. So when you were showing the example with the C2V molecule, you are creating the symmetry table, the multiplication table. And I was wondering, what if the molecule is centrosymmetric? How it's done? Is it like there is another argument added to the function, or is it something else that is done?
What do you mean with antisymmetric?
Centrosymmetric, like Gerade and ungerade.
Yeah, that's you can use whatever. I mean, there's no restriction to what kind of product table you put in there. So you can use here G and U, yeah. You can use C2, you can use C2V. Any abelian group is fine, and even non-abelian groups are okay, although you don't gain anything if you use a non-abelian group. So it's currently better to use only abelian groups, but you can set up any product table you want. You can also set up all possible product tables of all point groups you have at the beginning of your program, and then use whatever you need at the moment.
Okay. Thank you.